Ah, there you are, Andy. Are you all set?
Yeah, can you hear me okay?
We can, Andy.
Right.
Yep, so Andy's, whilst you're getting set up, I'll just tell people that you're, well, it's there now, but you're also from Loughborough University, and you can talk about AM of wooden dressings, and that's fine. So all yours, Andy.
Cool, thank you. So yeah, this is a project that we've recently started working with Richard Bibb. Yalis is the RA at my university, and then we're also collaborating with Shang-Chi and Bin Jiang, who are going to give a talk tomorrow, actually. So they'll be talking about functionalized materials, and I'm going to focus more on the sort of functionalization of the structure and the additive manufacturing process. So very briefly, wounds are not my area of specialty. I'm very much a mechanical engineer, but I like this image. Can you see my cursor at the moment? Let me.
It's quite small, but we can see it. If you, yeah, I was going to say if you made it something else, that would help.
Cool. Okay. You should be. If you can't see a little red laser pointer, let me know. And this wound,
it is more visible, Andy, so that's fine.
Perfect, cool, thank you. And this is nice and simple. We have some bad stuff out here, bacteria and viruses, and it's taken from a recent review article that obviously we want to keep out of the wound. So over here, they're just showing the wound is doing that job of keeping the bacteria and the viruses out, but also for sort of functionalized wound dressing, so the wound dressing, then the bacteria and viruses that may already be in the wound can be attacked by the body's natural defenses, but also by functionalizing with advanced materials and so forth to improve wound healing. So there's a couple of aspects of that will be taken forwards, and the obvious one for sure, complex materials, is what I'm not going to go into, but adding functionality, so those materials have got drugs in, antimicrobials and things, it is an obvious one. Then taking it forwards to multiple materials, those materials might have some challenges if they're highly functionalized. So then multi-materials allows us to combine those with more mechanical materials or more easy to print materials. And also allows us to do, say, different properties at different locations or at different layers within the structures. And I think that's a key thing for additive. We can change things within a layer and between layers. So if we want to have different pore sizes at different locations, it's just as easy as doing the same pore sizes everywhere, pretty much. And it also, of course, allows for that microscale geometry. What we're not talking about is nanoscale fibrous wound dressings. For this project, we're going to use off-the-shelf solutions for that nanoscale stuff that might wick away liquid and focus more on a sort of framework above those nanoscales, which may be fibrous dressings or could be hydrogels or so forth. Obviously, customization is a huge one in terms of the shape of the wound, specific materials for different patients, specific locations on the body, and that side of thing, and manufacturing on site. A very clear one with these printers. We're talking about extrusion printers, which are nice and easy to transport. So I'm going to introduce it all based on a bit of prior work, kind of that's been my focus over the last, probably getting close to a decade now, actually. I think it's relatively recent, but actually I'm settling in for quite a long haul at this. But it's custom G-code, which basically means the normal process, which we'll get onto in a moment, has a CAD model. You export that as an STL file, and then you slice it. And here we just skip all that. So there's no CAD model, STL file, slicer. We just tell the printer exactly what we want it to do. And when I'll probably mention G-code occasionally. G-code is just very simple text that is sent to a printer to tell it what to do. So in this command, G1, the printer reads that and thinks, right, I'm going to move somewhere, defined by X, Y, and Z, at a certain speed defined by F, and with a certain amount of material defined by E. So we're designing this code to actually get the printer to do what we want directly. That's what we're schematizing here. So as I mentioned, the CAD model, the STL file is just a kind of bad version of the CAD file, let's say. It's just a really simple file to translate between different softwares, but it has very little information. There are better versions of that, but they all have limitations. And then the key aspect for 3D printing, we take that, split it into layers, and for each individual layer, we then identify a particular print path to produce that layer. and that's then converted into the G-code. Whereas with the approach we're talking about, we just directly design that, which means if we have any problems during manufacture or want to optimize it, we have this feedback loop going directly to the sort of design, rather than having to go through to the CAD model and then through various settings, which allows for much better optimization. And a couple of sort of points about CAD. This type of structure over here is really easy to design a print path for, because you just move the nozzle in straight lines. It's really hard to create a CAD model for this and then take it into slicing software and slice it. It's the wrong way. It's not the appropriate kind of workflow for this type of structure. Same with STL files. This model would be represented as loads of tiny triangles around all of these individual extrusions, as opposed to the only information we really need from that is that the nozzle is going to move in one straight line. And then the third bit is about slicing. So even if we have a nice CAD model such as this with no defects, but the individual, what I've done here is print lots of cylindrical pillars with different wall thicknesses. And you can see when you have a wall thickness 0.4, which is the same as the nozzle diameter, prints it really well. When it's 0.6, the slicer is trying to fit kind of 1.5 lines in, and this is the actual print path preview. Well, you can see it does a circle, and then it kind of just botches in a few bits here and there with lots of movements to get there. So unless you really hone in your settings in your slicer, and you really can't to a truly optimal state, you're going to have this type of printing, as opposed to what is really easy to do is actually just print a line which is 0.6 wide instead of 0.4. So the way I've kind of evolved to do this is through a sort of software I've written, which is very open. It's mostly it's based in Excel at the moment, and I've got a Python version under development, which you basically describe what you want in terms of lines and things, and it will generate the G-code. So these are some examples from my website, which will give more details about the overall workflow if you're interested. So then for lattices, this is the type of structure that really started with the custom G-code in Loughborough. And then what this structure is, just a nice auxetic lattice. I think I've got one here actually. So as you stretch it, I don't know how well it's working, as you stretch it, it gets taller as well. And that's the auxetic nature. If we tried with the normal workflow, this model would just, it's really challenging to print, because as logical as this path it looks, where we're just going in one direction, going to the end, turning around and coming back, that information, that logic, it's not possible for slicing software to see that by looking at this structure, because it's designed for any structure that anyone might ever print. Whereas if we're looking at a more specific type of structure, like a 2D lattice, then there's a lot more kind of constraints that can be placed on it. And in this case, it's a challenging material because it's a flexible one. So actually stopping and starting printing is really bad. So here, designing that print path to be continuous all the way is really critical. So followed on from that, taking those lattices and then started printing on some kinesiology tape. This was my student last year who published this. Again, all the images and stuff have references at the bottom of the slides. And this was then taking it forwards from just a purely kind of interesting study to actually an application. So she was very much interested in the sports side of things and wondering whether we could customize this tape. And it really worked well. This force displacement or force strain plot shows the unreinforced tape, and then with different patterns on the tape of how they change. So they look kind of similar, but they are drastically different. If we look at 0.2 strain, you know, the force of the blue one is 2 to 3 times the force of the red and green, which would be these two. So that's with the interlocking. It's also auxetic, whereas these two aren't. So we can really change the properties beyond just force by actually printing onto this lattice. So this is quite similar to what we might do in some of the wound dressing applications, where we'd have specific requirements. They might be mechanical, like we're talking here, but they might also be about porosity or different materials with different drugs and so forth. And then I think this is the last slide I've got about the kind of the designing of these print paths in general. Maths is just a really beautiful way to design these print paths. So this spiral here that you can see the animation for, these plots on the right are just showing the values of x, y, and z, and they're defined by this equation over here, which is cos of t, where t is going from 0 to 1. And it's that simple. So if I can define my nozzle is moving according to these three equations, then I can print this spiral. And that's exactly what I've done here. But I've also, on top of that kind of spiral, which here it's doing, say, 100 layers of a spiral, I've also fluctuated the radius to get these. So these are just a very slightly more complicated mathematical equation than these. And they're just really, really simple to print. Taking that towards more practical, I mean, these are very practical for many applications, to be honest, but more conventional kind of impressive lattices. These are sort of gyroid inspired lattices where, again, we've defined this in much the same way in terms of X, Y, and Z to get these. So rather than doing a mathematical definition of a 3D model, we're just doing a mathematical definition of the motion of the print head, and you can really get proper good structures. So then a couple of examples of stuff in the literature, and I probably sound really grumpy and critical, and the research in these papers that goes far beyond what I'm talking. I've pulled out little bits of these papers as good examples of the kind of conventional limitations, but it's not to say that I think the papers are a load of rubbish. They're just good for me to emphasize my what I'm aiming to do. So in this paper, they're describing how you can vary pore size and also vary porosity. And the conventional way to do that is if you print lines, and then if you separate them further apart, you'll get bigger pores. If you'll get more porosity as well. But you could also print thicker lines with the same spacing, and that would give you a different type of property. So you can combine these two factors of how wide your lines are printed and how far they're spaced to get potentially the same porosity with different pore sizes, or different porosity with the same pore sizes, and so forth. And then they were saying for graded structures, you could combine these, and you can see over here the kind of CAD model that would then be generated with a wide section with a smaller gap, and then narrower sections with lots of gaps. But the problem comes when you try to go between these, because the overall kind of concept of additive manufacturing, just doing whatever you want and you don't need to worry about it, is really limits the quality, because you're getting defects that come in from that. So here you can see their algorithm to grade the porosity at different locations, and there are these kind of disjointed changes in where there is material and where there's not. And what that leads to is the nozzle kind of trying to jump around rather than print continuously, and it doesn't really get the structure that is actually intended. It does a kind of approximate job of grading, but it's certainly not printing the desired model exactly. And then you can see also over on this one, they've tried to do it with different gradings, and now you can see where the nozzle's kind of traveling and jumping across and causing all these defects and stuff. And that's the issue for especially extrusion additive manufacturing, of not having a nice continuous print path. Then a final one demonstrating some of the issues here. You can see stringing. It's a really common issue, especially when we go to more complicated materials, where they've got this 3D structure which they're grading as well. And you can see here how they're grading it. And this is a really common way to actually get a graded structure. You get your 3D model, and then you just grade your 3D model. There's loads of generative software and stuff that can do that. But it ends up with challenging printing, and the size is really restrictive. So here they're printing with unit cells were up to, I think, 30 times the nozzle diameter. So you're really looking at larger structures than what we can do with the nozzle. So typically, we print one line. That's our smallest resolution we can get. Here they'll be printing maybe 12 to 20 lines or something in the grid, and that's just because the normal way of printing, you tend to want a reasonably large area so that you can print an outline and then fill it with material. But it does then mean it's not very good if you're trying to do tiny things which is obviously good for medical applications. So then where we came with the idea for this project was taking it, the design to a different scale, where we're considering the print path right at the beginning of how we might get these different structures. So even if we print a single line, if we change its width as it's being printed, then this can lead to a nice defect-free lattice. So this was an example in a much larger overall paper about a kind of general capability to do this. And one of the case studies in that paper, which is called Convex, is shown down here, and the video on the right will show it shortly, where this is exactly the same print path in terms of it's always a square grid, but the width is being varied to get these different structures. So here it's just printing a constant rate. So we have a constant line width and we have a nice neat square grid. As we go through, these will change, so that now it's printing fast on the right and slow on the left. So we can get this different grading here. You can see for some of the other ones, we can fluctuate that in kind of interesting ways. And I think you should be able to hear the motors. I'm not sure if you can, but there's videos on YouTube for this where you can hear the motors going fast and slow. So this then allows you to have a kind of new way to control porosity. We're not varying the print path at all. We're just continuously fluctuating width to get this different ability, really. So then we can combine lots of different factors here. So there I've just shown you how we can get really interesting structures with the most simple of print paths, just a square grid. If we then take that square grid as an example, we can fit a square grid to a really complicated outline very simply as well. And this is using those lovely maths sorts of things that I was talking about earlier. I created this exact model and then transformed it to this shape. So now we could have our basic design might be a square grid. It could be anything else that we might start with a circle, start with triangle mesh or whatever, but we can morph it towards this customized shape. That's in plane. We can also do the same out of plane, and these are directly generated with my software, really, really simply. So we can now kind of combine complex shapes in a planar with non-plane, and also that video I was just showing you to really get a different sort of pores and shapes beyond what could possibly be imagined with the normal workflow of a CAD model, and then slicing it and so forth.
So Andy, you're over time now, so I can give you another minute or two.
That's it. Now this is my last slide for just acknowledgements. So yeah, taking that forwards now, it's really taking what I've just kind of shown you and applying it to the wound dressing application. And a big part of that is talking to experts and finding out what the most sort of beneficial capabilities are in terms of varying porosity or varying mechanical properties or anisotropic mechanical properties and so forth. And then really a large part of the project is about the drug release. So having different drugs at different locations and measuring their release and evaluating what kind of drugs would be good for different types of applications and so forth. So yeah, that's just the end of that. Thanks to the other people in the project. A couple of the images and videos were done by some of my students. All the others that I haven't acknowledged, they're in, I've given links to the papers. And then Shung will be giving her talk tomorrow, not specifically about this project, but very, very similar. Cool. Thank you.
Great, thanks, Andy. And that's us just essentially at the end of the first day. I'll just quickly bring up the agenda for tomorrow. So tomorrow we focus on pharma and regenerative medicine initially, and then look at sort of applications, if you like, so design processes that are being used on sort of current products to some degree, at least from a couple of the presentations. So seeing implementations out there in the field into the bargain, and so it's actually a fabulous list of presentations for tomorrow. So I'm looking forward to it and looking forward to the discussions that it prompts as well. Patrick or Alan or Richard, did any of you want to add anything before we finished up?
I think he's Alan.
Right.
It's Alan time.
Yeah, just going to say thanks to the group I was in. We sort of got cut off in our prime. We were sort of mid-flow, and then we were automatically yanked back. But no, it's good. That's great. Thanks.
Yeah, I think the timer creeps up on you, and suddenly you're halfway through a sentence, and then you cut off. 4 minutes isn't enough of a warning, Patrick. Yeah, I think thanks very much for everybody for today. Tomorrow's going to be another exciting afternoon. Really looking forward to it, and hoping we get a decent turnout for that as well. So yeah, look forward to seeing you all again tomorrow.
Yep, that's great. So I think it's just thanks everyone, and we look forward to seeing you all tomorrow.
Cheers. Thank you.
Thanks to everybody.
Thank you.
Bye.
Thanks, Kenny.